Hello, everyone, and thank you for taking the time to tune into this presentation. My name is Jonathan Perry, and I am a graduate student at the University of Texas, San Antonio. I'll be presenting ISEG, Fast and Efficient Few-Shot Semantic Segmentation. This work is authored by myself and Amanda Fernandez, my advisor and principal investigator at the Vision and Artificial Intelligence Lab here at UTSA. Before diving into this approach, I would like to mention that the order of this presentation may not be in the same order as it will appear in the paper. That being said, this presentation will cover the key points outlined before you, starting with outlining the challenge and the motivation for this work. I will cover related works and the contributions we provide with ISEG. Lastly, performance and results of our approach and planned future works. So if you are unfamiliar with the challenge, this challenge is the OpenEye Dataset Sparse Semantic Segmentation Challenge. This is the second iteration of the OpenEDS challenges, where this one has a primary motivation focused around accessibility of large amounts of unlabeled data with very few manually labeled samples. As the title of the challenge suggests, this data is comprised of head-mounted display video recordings of the wearer's eye, provided in sets of sequences with only a few of the frames per sequence manually labeled. The labels are comprised of 4 different class features per sampler image. That's your background, your iris, your sclera, or your pupil. This data set does have roughly 29,000 images, and only 2,600 of those images are labeled, and 1,000 of which are within a hidden test set. So to mention some previous approaches to similar problems and methods, including UNet, which UNet contributed a network with skip connections or residual connections for maintaining high-level or simple features. DeepLab showcased dilated convolutions where it expands the effective field of view for the convolutions. But more closely related to this approach are previous works produced through the first iteration of OpenEDS challenge, which showed very promising results leveraging neural networks focused on low amount of parameters. RATNet applied adaptive histogram equalization, a varying data augmentation technique, and a combined loss function. Mininet applied stack dilated layers into a encoder-decoder framework. So to go on to the ISEG framework, to take a high-level view of ISEG framework, specifically encoder-decoder framework, this network kept a consistent filter size throughout the entire network. As you can see, there's 4 encoder blocks and 4 decoder blocks. ISEG utilized residual connections within each block, and you can see that with those blue lines. This network was additionally built to be conscious of memory size to be employed on embedded systems for real-time environments. Being it's only 190,000 parameters, this can be considered a lightweight design and capable of that. To break down each of the types of blocks within ISEG, we can look at these dissections of the block. Starting at the encoder, the primary motivation for this design choice is the conditional application of dilated layers, you can see with the dotted line. Whereas the expanded receptive field will only be beneficial at certain stages of this architecture. This proved to have a significant impact on its performance through various tests and experiments we conducted. On the other hand, the decoder will follow a more simple design with a residual connection for retention of those simple features and early features, just like the UNet style design. Influenced by the success of RIT-NET's combined loss function, we applied a combined loss function with generalized dice loss and categorical cross entropy. This combined loss function demonstrated a massive increase for the iris and pupil categories specifically, where both the iris and pupil had an extremely small volume of representation compared to the other class features, background sclera. We employed two different training methods to ISEG. First, we established our own baseline, if you will, with a standard supervised learning approach, which actually performed really well given the amount of labeled samples, yielding approximately a 94% mean intersection over union. Second, we employed a semi-supervised learning environment using pseudo labels generated highly confident predictions, as well as the provided labels. Although this training method had promising performance increases with our local testing, we unfortunately did not have access to the hidden test set for this experiment to further test and compare between these two. To make a thorough benchmark of ISEG, we compared the performance of ISEG against the provided baseline from the OpenEye dataset challenge. And we also compared it against two of the previously proposed networks from the first iteration of OpenEDS. ISEG overall yields a 94.5% mean intersection over union. For additional comparison, we included the other class features individually, as well as the model complexity. As seen in the results table and the figures below, ISEG does perform well. However, there is a degradation of performance you can see in that bottom picture, as well as you can see in the results table under the sclera category, where this is apparent to be a challenging class feature. This could be solved with some of our future works, whether that is with a memory unit such as like an LSTM, or exploring other methods of domain adaptation or self-training. I believe that incorporating sequential information could mitigate the issues that we saw in that results section of ISEG. But this is all I have for you, and thank you for your time.